All right, so thermochemistry. This is kind of an introduction-ish to thermochemistry. This quote from Richard Feynman: "There is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact as far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes," meaning that every change in nature conserves energy. It always goes somewhere. Even if, right, if I take my Apple Pencil, maybe I won't do it with my Apple Pencil. I've broken that before by dropping it. If I take this marker and I drop it, right, it has some amount of potential energy, gets converted to kinetic energy, but when it stops on the ground, where does the energy go? It gets converted into heat. Yeah, there's some converted into the sound that it makes. Most of it is heat. And that's the conservation of energy. It always goes somewhere. And yeah, there's no way to break that law. So we're going to be discussing where it goes in chemistry and where it comes from. Where does it come from? Where does it go? Where does it come from? Cotton Eye Joe. So most hand warmers, right? Hand warmers seem to heat up by magic, but they're actually using a chemical reaction. And there's a lot of things that can change how much heat you feel from the hand warmers. If you've got thicker gloves, more of that heat gets trapped in with your hand. The size of the hand warmer is going to change that. But it is it's iron rusting fast. So you've got oxygen reacting with iron to form iron oxide, and that releases heat. So mostly that energy from that reaction is coming from potential energy stored in the bonds of iron and oxygen, and they release energy when they react to form new bonds in iron oxide. So there's less chemical potential energy in iron oxide than there is in iron or oxygen by itself. So I guess we could think of a lot of chemistry as we've studied it up to this point is the study of matter. But if there's no energy, then the matter doesn't do anything. So we also need to talk about energy and how that affects the reactions that do happen. So thermochemistry is that study. And we're going to be talking about thermochemistry, but also energy, work, and heat. So energy is the capacity to do work. So you have to have some amount of energy to do some work. Usually work is defined as a force acting over a distance. So like the typical example is to take something and like push it across the table, right? So I'm applying force, and I'm applying force over some distance. And so it takes some amount of energy to move this water bottle across the table from point A to point B. That takes energy to do that work. And then heat is the flow of energy caused by difference in temperature. So you're going to be doing that in tonight's lab. We should get that far. So that heat, that flow of energy caused by a difference in temperature, happens everywhere where there's a difference in temperature. So like right now, you are radiating heat out into the room. You're just losing heat, and it's fine because we can self-regulate our bodies, unlike lizards. We can regulate our body temperature. Warm-blooded, that's what I was looking for. Where lizards are cold-blooded. Yeah, literally everything. As well as you think your house is insulated, it's always losing heat to the outside. Or if you're trying to air condition inside your house, heat will be leaking in from outside somewhere, somehow. So we can think of energy as a quantity that an object or a set of objects can possess. So if you roll a billiard ball, it has energy due to that motion. When it comes into contact with another billiard ball, the energy is transferred from the first ball into the second ball, and that's work being done. And now that energy being transferred causes the second ball to go into motion. So we can move energy out of an object or into it. And I do want to kind of frame things here, like keeping with, we just covered gas laws and stuff in kinetic molecular theory. So when we think about gases, right, they have some motion, and the temperature of a gas is related to the kinetic energy that it has. That also applies to everything else. So we could measure the sort of kinetic energy of the molecules in this desk, in an iPad, in the walls, right? They're not moving in long straight lines and bouncing off of things, but they're vibrating still in place. So they have some kinetic energy in addition to chemical potential energy. So we can move that energy around, or we can change that energy. And so kinetic energy is the energy of motion. Again, most recently we've talked about that in terms of gases. Thermal energy is another type of kinetic energy, but we're talking about sort of the kinetic energy for a bulk object or material and how much kinetic energy all of those particles have together on average. And potential energy is energy that is stored in an object or energy associated with either the composition or the position of the object. So like the billiard ball being raised up over the table, or the marker that I lifted up and dropped earlier. And then chemical energy is a form of potential energy, which is associated with the relative positions of electrons and nuclei in atoms and molecules, which is a deeper thing. So we can take, well, I guess I should say this too, right? We can take either potential energy in general or chemical energy more specifically and convert that into thermal energy. We can unlock that in order to do work on things. Specifically, heating things up is what we're going to do today. So if energy is sort of the broad overarching concept here, underneath that we can sort into kinetic energy or potential energy, and then specifically with regard to chemistry, our kinetic energy that we're talking about is temperature related. So what is the average kinetic energy of, I guess when we're doing it later, the water, hot water and cold water, or the metals. And then also chemical energy, which is associated with the positions of electrons and nuclei. And yeah, we'll be sticking more to temperature, thermal energy. So the law of conservation of energy that Feynman was referencing in his quote means that energy can neither be created nor destroyed. So energy can be transferred from one object to another, or as the example here, dropping the billiard ball or dropping the marker, anything that really comes to a stop, even though it had kinetic energy, most of that energy is being converted into thermal energy. Another way you can sort of visualize this is if you compress a spring. I feel like this spring here would be really fun, but also super dangerous. Because if you slip and the spring pops up and punches you in the face. Yeah, that's would not be allowed on playgrounds. That's for sure. But here we're taking this ball and you're compressing the spring, and the spring is able to store the kinetic energy, like the force that you're adding to it, it's able to store that. And then when you let go of it, it reconverts all of the potential energy that it's stored back into kinetic energy, sending the ball flying. Yes, boing, boing. Right, so lots of ways that we can transfer energy around. So we're going to be studying, this is kind of, I guess, is the only way you can really study it, but with regards to energy, heat transfers, we're going to be looking at really a system and then the surroundings. Because it's way too complicated to consider the fact that if we turn on a hot plate in here, it will warm up the air, and then that heat travels out, and then it starts to warm up all the walls, and then beyond the walls, it starts to warm up outside, and you can get way too far out, because we don't care about all of that other stuff. We care about whatever our system is and the immediate surroundings. And I guess even going further than that, Right, our system will be like our calorimeters today, the hot water and the cold water. That's the system that we're concerned with. Anywhere else that the energy goes is the surroundings. So if you, like today, you'll probably notice we'll calculate the calorimeter constant, so how much energy the calorimeter absorbs. But I think even if you take, well, if your measurements are accurate enough, if you measure the temperature of the cold water, hot water, you pour it in there, even accounting for the calorimeter constant, you're still going to come up a little bit short on energy. Partly because we're going to be using coffee cups for calorimeters, and those are okay, but there's always some energy that gets lost to the surroundings. So unless you've had a calculation error, any shortcomings in accounted energy are going to be lost to the surroundings in general. And it's just gone then. So we can think of this conservation of energy, and again, if we're thinking of energy as a quantity of something that an object can possess, it means that the amount of energy gained or lost by the system has to be equal to the amount of energy lost or gained by the surroundings, conversely. So if we have our system energy gauge and our surrounding energy gauge, some heat transfer or energy transfer happens. Now our system has less energy and our surroundings have more energy. So I guess to extend this context, or extend this concept, when you plug something into the wall, where does that energy come from? The power plant. And it's being transferred all the way here. But where does the energy in the power plant come from, most likely? Huh? Yeah, how do power plants generate electricity? Water. How do they make the water release energy? Boil it. Yeah, I mean, okay, yeah, let's talk conventional power plant. Let's not talk wind turbines and solar panels. Oh, we could. Yeah, so right, the electricity here has to go through power lines back to the power plant, and in the power plant, they're heating up, they're boiling water, and that turns a turbine to generate electricity. Where does the energy to heat the water come from? Fire. Where's the fire come from?
Burning coal.
Burning coal, yeah, coal, natural gas probably in California. And so where does the energy in the natural gas come from? The chemical bonds. Where did that energy come from? Let's just keep going. Where did the fossil fuels come from? Dinosaurs. Where did the dinosaurs get their energy from? Plants. Where do the plants get their energy from? The sun. So it's photosynthesis with extra steps. So basically all of the energy on Earth, except for geothermal. Geothermal's a little bit different. That's coming from, well, it's heat radiating from the core of the Earth. There are some radioactive elements that are in the core. As those decay, they release energy from the associations of the electrons and nuclei and all that good stuff. Right, so basically the energy has to come from somewhere, and if it's coming from fossil fuels especially, it's coming from the sun. If it's coming from photosynthesis, or if it's coming from solar panels, it's coming from the sun. If it's coming from wind, where's it coming from? Where does the wind power come from? And what causes that? Causes differences in temperature. The sun? Basically, the sun isn't responsible for a lot of the climate, right? The sun rises, especially if you're on the coast. Nuclear is again like a lot of, I don't know what the proportion of energy in the Earth's core is generated by nuclear decay, but it's a similar thing where actually, no, nuclear is more direct than that. We're really on a tangent today. That's okay. So this equation, E equals mc squared. What's E? Energy. What's M? Mass. And what's C? Speed of light squared. So it's like 3 times 10 to the 8. This mass, this is matter being converted into energy. Nuclear energy comes from the mass defect. So when you do when a nuclear reactor, well, we'll say nuclear reactor instead of a bomb, when you're generating power in a nuclear reactor, every single one of those fission cycles is converting some small amount of mass into energy. So we're consuming matter to generate energy in nuclear reactors. Any nuclear process is going to have some, it's called a mass defect, where there's some unaccounted for mass that gets converted into energy. So that's why that equation is actually so special, because it defines that relationship, and it does it in like a really small sentence, or I mean equation. So all of that to say, right, and then that's again why we only consider our system and its immediate surroundings. So to transfer energy from one place to another, and we're going to be using essentially photosynthesis with extra steps to heat up the hot plates to add heat to your water, and also whatever metals that you have to heat up. Sorry, quite the tangent. So after our energy transfer, that heat has to go somewhere. The energy goes into the surroundings. So all of that heat that you generate today on these hot plates will end up just going into the surroundings and dissipating. Okay, so let's talk about units of energy real quick. So an object of mass m is moving at a velocity v, has kinetic energy of ke, given by this equation. So we can take kilograms meters per second. The SI unit for energy is the joule. And that's 1 kilogram. So the mass there would be kilograms. And then velocity, v, is meters per second. And we square that. That's meters squared per second squared. And so that's how we get this unit of the joule. So 1 joule is actually a very small amount of energy. A 10-watt light bulb, it's a very dim light bulb. Well, it's a dim incandescent light bulb. It's fine for an LED. Most LEDs, I think, like an LED light bulb will be about 10 watts. And that'll use 36,000 joules in 1 hour. So 36 kilojoules. And we can also take that, and if we convert it into units of work, which is watts, specifically kilowatts, so that 3.6 times 10 to the 4 joules is 0.01 kilowatt hours if that light bulb's on for 1 hour. And that's what PG&E measures your electricity in and charges you by. Ask me about time of use plans later, and I'll tell you how they're a scam. So joules is our unit of energy. Another unit that doesn't get used very often, except when talking about nutritional things, is the calorie. So the calorie is actually, well, originally defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree C. So if you get a gram of water and you heat that up and the temperature of that raises by 1 degree C, you've applied or added 1 joule of heat to that water. Huh? Sorry, 1 calorie of water, 4.184 joules. Thank you. The calorie that is used on the back of nutrition labels, right? On nutrition labels, I should say, is calorie with a capital C, and it's 1,000 lowercase c calories. So you can actually measure your energy intake. Just got an idea for a question. It's mostly just a conversion thing, but this is one of the silly things that you can do with conversions. So you could calculate, in a sense, if you need to eat 2,000 calories a day, and then there's 24 hours in a day, you could calculate how many kilowatt hours you use in a day.
How many light bulbs?
And then, yeah, how many light bulbs worth of electricity you use, how much PG&E would charge you to be alive, if you ran on electricity, right? You guys can do that later.
Can't afford it.
Yeah. It's probably not very much. The human body is pretty efficient. So the units that we're going to be using are going to be joules. But it's important to know that the calorie exists, and that a capital C calorie is 1,000 lowercase c calories. Some conversion factors between these. You might be able to just use one of these for doing that conversion. Wait, that's, 2.5, 250 kilowatt hours. Okay, so those are units of energy. So the first law of thermodynamics, another way to say this is there is no free lunch. So as we walked through the ridiculousness of the energy grid, that energy came from the sun billions of years ago, or whenever dinosaurs were around, right? And then those dinosaurs died and their energy got trapped underground and then was compressed into what we know as fossil fuels, and we burn those to drive our car to get McDonald's. So that energy comes from somewhere. And this one's kind of wild. The total amount of energy in the universe is constant. So you can never design a system that will continue to produce energy without some source of energy. So there's no such thing as a perpetual motion machine, because there's always some amount of energy lost to friction or air resistance. There's always a motor involved in those things. So with energy, you can't get something for nothing. You have to spend energy to make things happen. Right, state functions. State functions are kind of a weird thing. So a state function is a function where the path that you take to get from A to B doesn't matter. So if you're climbing a mountain, it doesn't matter if you walk straight up the side of the mountain or if you take a winding path up the mountain. In the end, your elevation at the top of the mountain will be the same. Doesn't really matter how you get there, as long as you get there. That's a state function. So the difference between the initial and final values doesn't matter, or is the only thing that matters, not the path taken. So internal energy of a system is a state function. So we define the internal energy as the sum of the kinetic and potential energies of all the particles that compose the system. Meaning that, okay, so I guess one step back, right? The only types of energy, what are the types of energy that we have? Kinetic, thermal is kinetic, and potential. So there's only kinetic and potential energy. So the kinetic and potential energies are all of the energies that we can describe in a system. So all of the possible energy is the sum of those two things. So increasing or decreasing the value of the energy in a system, right? We can heat it up and add thermal energy, or we could have a chemical reaction happen, and that can either release energy or it can actually absorb more energy. That's just a state function. If you know what the energy is at the end, you do something to the system, and it has a new energy after that. The difference in energy is the difference in energy. It doesn't matter how that energy gets added. So here the delta, and we'll see this in the heat capacity equation too. Delta means a change in. So the change in internal energy is delta E. I guess actually one example of this would be like, so if I take this marker, I can add energy to this marker by lifting it higher. Now it's got higher potential energy. I can also increase the energy of this marker if I hold it here and then I hold it in my hand and warm it up. the internal energy of this marker will increase because it's got higher thermal energy. But it doesn't matter if I raise this or if I heat it up. Those are both changes in energy, and both will result in increases in the energy. Just how much you heat it and how much you lift it determines what it is. Yeah, kind of like a bank account. Doesn't matter if I buy, I guess McDonald's is my example today. It doesn't matter if I go out and buy McDonald's or if I buy, I guess, Burger King, or if I go out and I go to somewhere somewhat healthy in Panera. If I spend the same amount of money at all three places, I've spent the same amount of money. It doesn't matter what I'm buying with that money. So I guess you could say your bank account is a state function. Doesn't matter how you empty it. It'll be empty at the end. So for chemical reactions in a chemical system, right, the reactants constitute the initial state and the products constitute the final state. And so here we can define the change in internal energy as the difference in energy of the reactants or products minus the reactants, the difference between the two. So for some reactions, we'll have reactants with a higher internal energy, and then after that reaction, the product will have lower internal energy. And this would actually be the reaction that happens in like charcoal, reacting carbon with oxygen, and that releases heat. So you're losing energy from that system in the form of potential energy. So your system is negative, loses energy. Your surroundings gain any energy that your system loses. It always goes somewhere. And in the same way as like climbing up or down a mountain portrays sort of your potential energy or your altitude on that mountain, that's how internal energy diagrams work. So this arrow is showing us that up means higher energy. And so if we go from a higher energy to a lower energy, then we've lost energy from our system. So again, we have higher energy for the reactants, lower energy for the products. And so you always have to think about this in terms of the system and surroundings. And so if your system loses energy, then that energy is gained by the surroundings, and vice versa. Just like transferring money through accounts. And we could actually, well, you could potentially reverse this reaction. There has been some work to turn carbon back into fossil fuels, or fossil fuel-like compounds. So if we could reverse this reaction, then we would be taking our CO2, which was the product, now the reactant, and essentially put that energy back into it and get what were our reactants, now our products. That just reverses. The change in energy is the same, but now we've flipped the signs. So our energy, our system here is gaining energy, and that energy would have to come from the surroundings in one form or another. So to put that in terms of today's lab, you'll have some metal in a test tube, and essentially, the metal in the test tube is your system. Your surroundings is going to be boiling water. And so, well, I won't go too far with it, but heat comes from the hot plate, goes into here, heats up the water. That heat then is transferred into the metal. So the energy lost from the surrounding boiling water, lost from the hot plate, would be gained by the metal in this case. And since we can heat this up to a constant temperature in boiling water, we can take that metal, if we know the initial temperature of that metal, dump it in a known amount of water, and we can measure the change in temperature of the metal. Right? And so that temperature, what is temperature again? What type of energy? Or I guess change in temperature, yeah, would be thermal energy or kinetic energy. And so we'll be flowing kinetic energy from the hot metal into cold water. So the reactants have higher internal energy than the products in terms of these energy diagrams. The delta E of the system is negative and energy is flowing out. So if reactants have higher, keeps doing that. Nope, I don't want to highlight the whole thing. Higher, so if reactants have higher, then delta E is negative. What is happening? Okay, I don't know what that bar is at the bottom. Oh, there we go. And if the reactants have lower internal energy than the products, then the delta E is positive and energy is flowing into the system from the surroundings. So again, it's like money or your bank account. Right? Money leaving your account, a withdrawal, is negative. Money going into your bank account, which is always better, is a deposit. That'll be a positive value. Okay. So if we somehow had magical internal energy gauges for a chemical system and its surroundings, we're starting with this gauge up top. Which energy gauges correspond to the final conditions following an energy exchange in which delta E system is negative? So delta E for the system is negative. Is the energy flowing out of the system or into the system? Flowing out of the system. So where does the energy have to go? To the surroundings. So is it A, B, or C? A. So what's wrong with B? Yeah, the chemical system's energy goes down, but somehow it doesn't go into the surroundings. And black magic is at play. One way to spot a witch. She breaks the law of thermodynamics. Sorry, I don't know. And what's wrong with C?
It's the energy of the system is positive.
Yeah, energy of the system there would be positive. It's coming from the surroundings back into the system. Because this is delta D is positive. All right. So heat and work. Yeah, so energy is exchanged between the system and the surroundings through heat and work. So Q and W are not state functions because their value depends on the process. So if Q is going to be positive, if Q is positive, then the system gains thermal energy. It is gaining kinetic energy. If it's negative, then the system is losing thermal energy. If W is positive, that means that work is being done on the system. So the system is being moved, and its energy is being increased by being moved. Or I guess work is being done on it because it's being moved. And negative means that work is being done by the system. And these, you can kind of think of these signs here in terms of delta E. So yeah, the sign of delta E has to be positive if energy is flowing into the system, and then it's negative if energy is flowing out of the system. So if we look at some examples here, the energy being lost by the white billiard ball is gained by the surroundings. So we take our ball, and the ball is our system here. And so it's losing heat, because as it rolls, it's slowing down, and it loses that energy to the surroundings. And then when it collides with the purple ball, because our system here is just the white ball, it also loses that energy to the white ball after it collides. So Q here is that heat lost. So it's the same thing if I took this marker and I drop it, right? That's being converted into, I guess in that case, it would be all converted into heat. But if I drop this and it hits something else and it moves that thing, then it's done some amount of work also. And so if you're doing work on something, that means you're losing energy, and so that's why the work is negative. Even though it is maybe a little less intuitive than heat being negative if you're losing heat energy. So if the billiard ball table is not as nice, and it's a rough table, you're going to end up losing more of that energy to heat. And so your energy loss to Q is higher, but you still end up losing all of the rest of the energy to any work that's done on the purple ball. So in both of those cases above, we have the same amount of energy in the white ball initially, but because of the path that the ball took, because of the surroundings around the ball, it lost energy in different ways. The change in energy in both cases was the same. It's a state function, so it doesn't matter how we lose that energy or gain that energy. It just matters how much is gained or lost. But depending on your circumstances, you're going to lose more energy either to doing work or to friction. Okay. Perfect. So a cylinder and a piston assembly, that's our system. And I'm going to draw another excellent piston. So this piston is warmed by an external flame. The contents of the cylinder expand, doing work on, all right, well now you gotta get a little artistic with it. So we've got flames, excellent flames. We got flames that are heating up the piston assembly, and so, stop. Our piston, or the gases in here start expanding, doing work on the surroundings by pushing the piston outwards against the external pressure. The system absorbs 559 joules of heat and does 488 joules of work during the expansion. What is the value of delta E? So I should hide the answer in the top corner. So we do the more intuitive one first. Is heating the system going to increase its energy or decrease its energy? Yeah. And you can also think of, right, so remember that we even have a gas here, right? So the average speed of the gas in the cylinder is kinetic energy. So if I take a marker and let's see, where can I lob this safely? If I just toss this, right, that took an amount of energy to just throw a marker. But if I throw the marker, is that more energy or less energy? More. Because I threw it, it went faster. It took more energy to make that marker go faster. So inside the cylinder, we've got all these little particles, and they're moving around. And when we heat this up, we're adding energy to them. So you could almost imagine that at the bottom of this thing, there's a bunch of guys, and every time a particle comes and gets close, and it hits this, it transfers energy to it. So there's a bunch of little dudes down here who are punching all the particles and making them go faster. So it's increasing the kinetic energy of all those particles. So by adding thermal energy, you're making all the particles move faster. And throwing something faster takes more energy than throwing something slowly. Right? So heating this does increase the energy. So that'll be a positive 559 joules. Neat. Love that. This usually fixes it. Okay, and we back. So adding that heat in there makes those particles move faster. So we're adding heat to the system. Now, what about doing work? So when I take the marker, and if I'm the system and I throw the marker, did I gain energy or lose energy by throwing the marker? Yeah, and you guys gained energy because you woke up because I'm throwing things. So you're the surroundings. So if the piston is doing work and it's pushing the cylinder out, is it gaining or losing energy by doing that? Losing, right? Because it takes energy to push that cylinder out. So then we would subtract 488 joules. So then our total energy change, it's just the difference between those two, because I don't even really need it. So 559 minus 488 should be 71. Yes, it is. Okay. 71 joules. And so you're also kind of doing a similar thing where we're, again, taking this, you're going to take the hot metal. This is just one of the steps. But you take the hot metal and you put it into the cold water. And then this hot metal has a lot of kinetic energy. Now, it's not like a gas where their particles are like flying through the air, but the metal atoms are going to be vibrating more violently because of that heat. And then when you add them to the water, they transfer those vibrations essentially, I guess you can think of them as hitting the gas particles that run into them and then knocking them away faster than they were going before. So that heat energy is being transferred. So you can almost say that the metal is kind of doing work on the water, losing that thermal energy. All right. So heat. Oh, yeah, we have to talk about this. Because heat is the transfer of thermal energy between a system and the surroundings, again, caused by difference in temperature. Now, the way that we talk about heat is a little bit weird in English, at least, because when you leave the door open, people will say, well, usually somebody will say, you're letting the cold in. There's no such thing as cold. There's only the absence of heat. So when you leave a door open, you're not letting the cold in, you're letting all of the hot out. And so all of the warm air particles that are in your house or in your room or whatever, they're leaving out the door and they're being replaced by colder, slower moving particles in the room. So when we're talking about heat, it's the movement of the energy. Cold is only the absence of energy. Did that break that, or is that still working? Nope, that broke that. Okay. Cool. Okay, so and then heat always is going to flow from higher temperature to lower temperature. And so that's why if it's colder outside than it is inside and you open a door, then the heat starts flowing to where it's colder. The reason it doesn't do it that fastly, if your doors are all closed and you've got decent insulation, is because that insulation slows down that transfer of heat. Those insulating layers are bad at transferring heat, which is good for us. because then you don't have to spend as much money heating things up. So ultimately, temperatures will become equal at a thermal equilibrium, right? Because even if you take this hot water and you heat it up to boiling, if you leave it long enough, it'll come back to the same temperature as the room. And that'll be a thermal equilibrium. It might increase the temperature of the room a little bit, but because there's so much more surroundings than there is hot water, it's probably not going to be measurable. Okay, so temperature changes in heat capacity. We're finally getting to what we need for lab today. When a system absorbs heat, its temperature increases by delta T. So there's a change in temperature. The increase in temperature is directly proportional to the amount of heat absorbed, and that's going to depend on the material that's being heated up. So there's a proportionality constant called the heat capacity, and that's going to have units of joules per degree Celsius or joules per Kelvin. So again, what is temperature? What does temperature measure? Thermal energy, the average kinetic energy of a substance. So there's some amount of kinetic energy there. So we're talking about something having a heat capacity. That's the amount of extra energy you have to add in order to increase the average temperature of that substance. So some things are going to be harder than others. Water has one of the highest heat capacities of a pure compound, 4.184 joules per Kelvin or joules per degree C. So it requires a lot of energy to be put into that system to make those molecules move faster in order to increase the temperature. And so that's why we can only use, well, how do I want to say this? So measuring the difference in temperature is kind of like measuring the difference in energy. And since that's a state function, as long as we can measure an initial temperature and a final temperature, we can calculate using C the amount of energy that it took to increase the internal energy of that system. So that's what heat capacity is. And generally we do this, so this is the general heat capacity. We're going to talk about specific heat capacity. Generally when that's reported for a substance, that's per, or increasing the temperature of that system by 1 degree C. Okay. Wait, before I go on, what do you think's missing from this equation that would be really useful to know? The mass. Because what happens if there's more mass? Yeah, if there's more mass, then it takes more energy to heat that thing up, right? Heating up this amount of water is going to take longer. I don't have another amount of water. Well, comparing this to like if you're going to make pasta, right? You're going to cook pasta, you need a whole pot of water. Versus this is going to take less energy. There's just less stuff to get moving. There's less particles that you have to give enough energy so that they're moving fast enough so that the temperature raises. So heat capacity may be useful for comparing things, but not as useful for calculating things. Yeah, so the larger the heat capacity of an object, the smaller the temperature will rise for a given amount of absorbed heat. Because it takes more energy, because you're increasing the average kinetic energy of those particles. And if it takes more energy to do that, the temperature is not going to rise as fast. Yeah, and this is the core of the problem with just heat capacity. So regular heat capacity is an extensive property, which means that the amount of energy that it takes is going to depend on how much of the thing you have. Heating up lots of water is harder, takes more energy than a little bit of water. Specific heat capacity is how we translate that into an intrinsic property. So to say, we add mass to it. So we say now instead of just being the joules per degree C, it's joules per gram degree C. So how much energy does it take to heat up 1 gram of this thing? And then if you know, well, if I have 100 grams, it's going to take 100 times more energy. If it's 1,000 grams, it takes 1,000 times more energy. And that'll depend on the type of material also. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree C. And then we can even calculate a molar heat capacity, so the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree C. Both of these are intensive properties, meaning that they don't change with the amount of mass. What's another intensive property that we've studied? Density. Density is an intensive property. It doesn't matter how much water you have, the water will have a density of about 1 gram per milliliter. Because as you increase the amount of water, you increase the volume, and you increase the mass at the same time, and so the ratio between those two doesn't change. All right, so specific heat capacity. Much more useful than regular heat capacity. And now we get Q equals mc delta T, which if you were here early enough, we discussed would be a really, really cool science-based wrapper name. mc delta T. I think I'm gonna have to take that. I'm gonna have to use that. Make that my gamer tag on something. And we've got some different specific heat capacities here on the right. So, yeah, we'll come back to that equation there. We'll look at these first. So you can see some things like lead or gold have really low specific heat capacities. So it doesn't take very much energy to increase the temperature of 1 gram of gold by 1 degree C. But then you go to things like ethanol, takes a little more energy, a lot more than gold. And even different metals have different heat capacities. This is why if you have even a cast iron pan, doesn't take that much heat energy. Like if you put that on a stove and you turn on the stove, it's going to heat up pretty fast. As soon as you add any amount of water to it, now you're trying to heat up the pan and the water, and it's going to take a lot longer. It's going to take a lot more energy. And the units here are especially useful because if we look at our Q equals mc delta T, I want to write grams times joules per gram degree C times degree C, which is delta T, right? The change in temperature will give us a temperature in degree C. If we multiply all of those together, the grams cancels, the degree C cancels, and so you get units of joules for heat. Pretty easy to use. Okay, so yeah, temperature changes in heat capacity. One of the reasons that it's so much warmer here compared to San Francisco, or even I guess if you went like straight across like Monterey, is because around here all we have is dirt. And dirt has a pretty low specific heat capacity. But if you go over to the coast, now not only is the sun warming up the dirt, but it's also warming up all of the water. And so all of that energy that gets absorbed by the ocean doesn't raise the temperature of the ocean very much because it takes so much more energy. And actually, I'm surprised it's not in the slides. So yeah, well, it'll be 68 degrees in San Francisco. It'll be 100 degrees here. There are also two places in the contiguous, or I guess not contiguous, in the United States, there are two states where the temperature has never gotten over 100 degrees. Can you guess what one of those is? Or you guess, you'll never guess the second one. So what states have never seen temperatures, or have actually in areas of the state, have never seen temperatures over 100 degrees? What? Where? Michigan has. Good guess. Thinking north. What else? Alaska is one of them. The other one is Hawaii. Yeah, Hawaii apparently I don't know how recent the, no, because I Googled it. I Googled it, and at one point in like 1923, it was 100 degrees Fahrenheit. It didn't get over 100 degrees Fahrenheit. So because it's such a small landmass compared to the ocean around it, the ocean absorbs all the energy. The temperature doesn't raise very much. And then Alaska, of course, is because it's so far north that the sunlight is so indirect, just doesn't warm up, especially northern Alaska. This is also the reason, I guess maybe there are other reasons too. We use water for generating electricity because it can essentially store a lot of energy, and then when it converts into steam, that steam can have a lot of energy, and then that turns turbines and we turn that into electricity. All right, so let's calculate something real quick, and then I think we've gotten far enough we can go to lab. We should do a couple of these. Oh, right, a lot of exposition. So to determine whether a shiny gold-colored rock is actually gold, a student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. And then she finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees C to 57 degrees C. Find the specific heat capacity of the substance composing the rock, determine whether the value is consistent with the rock being gold. How do we calculate the specific heat capacity? Mass, temperature change. And actually, without even writing down Q equals MC delta T, what are the units of specific heat capacity? Joules per gram degree C. So what if I told you that just using that, we could put those numbers in and get the correct answer? Because we were given joules. So if I take 57.2 joules, and I divide that by the mass, 4.7 grams, times the change in temperature, this is key. It doesn't have to be the change in temperature. 57 divided by, so 32 degrees C is the change. Oh, I guess we only have 2 sig figs. So what are the units of that 0.38? Joules per gram degree Celsius. So if we had taken, if I take Q equals MC delta T, and if we rearrange that, we'd get Q over M delta T equals C. So that's exactly what we put over here. What happens, what's the change in temperature if you do it in Kelvin? Yeah, if you convert everything into Kelvin, you're going to get the same number, because it doesn't matter what like the gross value of the number is, what the whole value of the number is. It's just the difference between the initial and final. And that difference is going to be the same whether we're in Kelvin or we're in degree C. Yeah. 1 Kelvin is the same, I guess, increase in temperature as 1 degree C. Yeah, so they're the same increments. Oh yeah, is this gold?
No.
We can go back to the table here. Yeah, gold's 0.128. Yeah, so most likely copper. Maybe something else. Maybe somebody painted a copper rock with yellow paint. Spray painted it gold. Yeah, what's the specific heat capacity of pyrite? It's giving me, all right, well, it doesn't want to give me like a specific number, so. All right, so, yeah, 0.38, and it's not gold. Copper, maybe? Okay. So we'll do one more of these. A 55-gram aluminum block, initially at 27.5 degrees C, absorbs 725 joules of heat. What is the final temperature of the block of aluminum? A couple things that we need, huh? So this one probably would just write the equation out. And I think that one of the key things for this is remembering that delta T is itself a little equation. Right, it's temperature final minus temperature initial. So MC times temperature final minus temperature initial. So, oh, that's right. Another thing that happens in these kinds of problems, we're told that the aluminum block is absorbing 725 joules of heat. So what's the sign of that heat? Is that going to be positive, negative? Positive. Yeah. So negative would mean that, so our system here is the aluminum block. Negative would mean that the heat's leaving it. Positive means that it's gaining it. So this will be a positive 725 joules equals 55.0 grams. Yeah, we need the specific heat of aluminum.
0.903.
Yep, 0.903 times temperature final minus 27.5. So the easiest way to solve this is do everything outside of the parentheses first. So we can multiply the 55 times 0.903. That's going to give us 49.665 times T final 7.5, and this will be 725. So then we divide 725 by 49, and that's 14.5978 equals T final minus 27.5. Add 27.5 to both sides. And 42.1 degrees C equals temperature final. And does that number make sense?
Yeah.
Why? Huh? Yeah. If it's absorbing heat, then we would expect the temperature to go up. So our temperature did go up. 42.1 is higher than the initial temperature. 42.1. Cool. Okay. Yeah. Just real quick, let's talk about this because it is relevant for the lab. Can we calculate the energy of a system from just directly from its temperature? Like if I told you that this marker is, let's say 21 degrees Celsius, can you tell me how much energy there is in this? No, not really. Now, if I heat this marker up from 21 degrees Celsius up to, I don't know, 30, whatever body heat is, 30 degrees Celsius, could you tell me how much energy it gained? Right? So we can use differences in temperature to sort of infer how much energy has been transferred. So that's why like this lab is all about like measure the initial temperature, measure the final temperature, and you can calculate how much heat was exchanged. And that's because we don't really have great ways of directly measuring thermal energy transfer. Like how much energy travels through the air from here to over there, and it's just not an easy thing to measure. Except by indirectly measuring it through changes in temperature. So that's why this lab is all about basically loading up different materials, water or the metals, kind of like a battery, a heat battery, right? We can take this metal, load it up with some amount of heat, stick it into something else, and see the temperature change as the energy is transferred from the hot to the cold. And then when we get that difference in temperature, we can calculate how much heat was lost by this and gained by the other. Okay. I think that's all we need. That's all we need today. Yeah, so you can set up equations equal to each other like this. We're ready for lab.